So we're going to get started with a typical example of what we would get when obtaining the maxima and the minima of a polynomial function, and then eventually the concavity intervals and the point of inflection in order for us to be able to graph this function. So the first step that we're going to have is to obtain the critical points. We have our example over here with a function of grade 3. So we're going to start with the critical points. If you remember, when obtaining the critical points, the first step is to obtain the derivative of our function. So we're going to get f prime of x equals to 3x squared minus 8x plus 4. After we do that, what we're going to do next is we're going to make this equal to 0 and solve for x. So I'm just going to rewrite everything. And we're going to make it equal to 0. Now the easiest way to do this in this case is with our general formula. So minus b plus minus the square root of b squared minus 4ac over 2a. So I'm just going to go ahead and substitute that. So I'm going to get 8 plus minus and then the square root of, in this case, 64 minus 4 times 3 times 4 divided by 6. Okay, after we do this, we're gonna obtain a result of 8 plus minus 4 over 6. So we're gonna get two results over here, x equals to 2 and x equals to 2/3. These are gonna be my two critical points, my first step into the procedure. Okay, so after we have obtained our critical points, what we're going to do is we're going to create intervals where we can test the behavior of these critical points. So what we're going to do is we're going to write an interval from minus infinity to the closest of these 2 points, so 2/3. Then from 2/3 to 2, and then from 2 to infinity. Okay. I'm going to choose an arbitrary value that is within these intervals. So in this case, arbitrary values that are easy to work with. I'm going to choose 0 here. Over here, 1, value in between these two, and last one between 2 and infinity, I'm going to choose 3. These are arbitrary values just to see more or less the way they behave. And what I'm going to do is I'm going to substitute these arbitrary values in my derivative, in my f prime of x, which we already know is 3x squared minus 8x plus 4. So I'm going to substitute for each of these. So in the first case, I have 3 times 0 squared minus 8 times 0 plus 4. Over here, 3 times 1 squared minus 8 times 1 plus 4. And in the last one, 3 times 3 squared minus 8 times 3 plus 4. I'm not really interested in the final value of these functions, but I'm interested in the sign that we're going to get in each of these cases. So over here, we're going to get 0 minus 0, and at the very end, plus 4. So we get a positive sign. Plus 4 is positive. Over here, 3 minus 8 is minus 5, plus 4 minus 1, so we get a negative value. And then in the last case, we have 27 minus 24 plus 4. Again, we get a positive sign. What we want to see is the way our function behaves in the different intervals. So if we have a positive sign, that means our function is going to be growing or increasing. If we have -1, decaying or decreasing, positive again, increasing. So in the very end, what we're going to get over here is growth intervals, wherever we have a growth pattern. So from minus infinity to 2/3, and then from 2 to infinity, and also decay intervals, for which we only have one, from 2/3 to 2. Okay, so from the information that we get in the growth and decay intervals, we can see that we have negative values that are increasing up until the point where we get over here, which is 2/3. And then it starts decreasing up until this point, which is 2. As we can see, we're going to have a local maximum and a local minimum over here. So we can just go right ahead and write them. Local maximum at x equals 2/3. Okay, right where it stops going and it starts decreasing. And a local minimum at x equals 2. So what we're going to do here is we can actually obtain the value for the exact point for this if we just substitute in our original function. So if we substitute in our original function 2/3 and 2, we're going to get our values. You can just do this with your calculator if you have the time. And you're gonna get minus 22/27 and minus 2. So at the very end, you're gonna be left with actual points for which you have 2/3, comma, minus 22/27 and 2, comma, minus 2. Now, our next step is to find the concavity, and the concavity is found with the second derivative. So that's our first step, to obtain the second derivative. So we start from here, and we're going to get 6x minus 8. After we have obtained our second derivative, we're going to make it equal to 0. So 6x minus 8 equal to 0. And we're going to obtain a value for x, which in this case is 4/3. We're going to do something similar to what we did in the second step, and we're also going to create intervals. So we're going to write an interval from minus infinity to 4/3, and then from 4/3 to a positive infinity. I'm going to choose an arbitrary value. And I'm going to use 0, and I'm going to use 2 over here. Okay, try to use values that are easy to work with. And we're going to evaluate these values in our second derivative, 6x minus 8. Again, to determine signs for each of the cases. So if we use 0, we're going to get 6 times 0 minus 8. If we use 2, 6 times 2 minus 8. And let's see what signs we get. 0 minus 8, we're going to get negative. 6 times 2, 12, minus 8, positive. We're going to get 4. And we're going to see that with these signs, we're going to get different concavities. If the sign is negative, we're going to get a concavity downwards. And if the sign is positive, we're going to get a concavity upwards. Okay, so we're going to do the exact same thing. Concavity upwards interval is from 4/3 to infinity, and concavity downwards interval is from minus infinity to 4/3. And then the next step is to find the point of inflection. We have a point of inflection wherever the concavity changes from upwards to downwards, or the other way around. So in this case, we're going to get a point of inflection at x equals 4/3. And we're going to evaluate that again in our original function to get the actual point. So f of 4/3. And we're going to get minus 38/27. So we get a point that looks like this. So the very last step is to graph our function. We have our key points, which is the local maximum, local minimum, and inflection point. We're going to locate them. So we have 2/3. which is around 0.7. So we have something here, and minus 22 over 27, which is around minus 0.81. So we have that point somewhere near here. The local minimum in 2 comma minus 2, so that's easy to find. And the point of inflection in about 1.33 and minus 1.4, so somewhere around here. We also need to analyze our intervals, our key intervals. So we have growth intervals from negative infinity to 2/3. That means that we're going to have an increased pattern from the left until we get to 2/3. Then decay interval from 2/3 to 2. So it decays from here to here. And then it starts increasing again. Okay. We also have our inflection point, for which we're going to get a concavity downwards from minus infinity to 4/3. So it's facing down in this part, and then a concavity upwards in this last part. So the only thing that we need to do is to connect our dots. So I have a concavity downwards in this part, something that looks like this. We get to the maximum, still concavity downwards, and then in the inflection point, we're going to change the concavity upwards. In the local minimum, we start increasing again, and then we just have a graph that grows.